Welcome to Genesis Engineers Academy, which empowers for better future. In this video, we are going to discuss on atomic structure, part 2, that is electronic configuration, all these things. So in the previous video we have discussed about quantum numbers, that is principal quantum number represented by N. Next azimuthal quantum number designated by L, and the next one is magnetic quantum number ML, and next one is electron spin quantum number ms. Okay, now so what principal quantum number tells us? It determines the size and also extent of the energy of the orbiter, and also identifies the shell, that is equal to n is equal to 1, that is called K shell, n is equal to 2 L shell, n is equal to 3 M shell, N shell, like that. Next, what is azimuthal quantum number? So this is also called as angular momentum. So it defines the 3D shape of the orbital, whether it is S orbital, P orbital and D orbital. The third is magnetic number. So this is the orientation of the orbital with respect to standard set of coordinate axes, that is x, y, z. So they are oriented, that is given by magnetic quantum number. And each electrons, this is about electron spin quantum number. So electron will rotate about that is about the nucleus in an orbit, and again along with that or besides that, this electron also spins around its own axis. It revolves, that is about nucleus. It rotates about its own axis. These are we have discussed in the previous video, part 1. Now we'll move on to that is next topic, that is this you have already known to you. If n is equal to 1, so if n is equal to 1, you have 1s. If n is equal to 2, you have 2, that is L is equal to 0, L is equal to 1, that is 2s, 2p. If n is equal to 3, so you have 3, so those are called 3s, 3p, 3d. You got my point? Like that you can have different types of these things. So for n is equal to 1, principal quantum number n, so you have L values 0, and if principal quantum number is n is equal to 2, you have 0 and 1. If n is equal to 3, you have 0, 1 and 3. So this we have discussed. Now the shapes of atomic orbitals. So these atomic orbitals are mathematical functions that describes the wave nature of the electrons or electron pairs in an atom. Wave nature. Okay, so this is a mathematical function and offers a way to calculate the probability of finding an electron in a specified region around the nucleus of the atom. So it calculates the finding the electron, where it is exactly located. The shape of s orbital. So the diagram is like a sphere. So the s orbital shape is a sphere. Okay, having nucleus at its center. In 2 dimension, it is a circle. So this is the general coordinate axis x, y, z, and this is the s orbital. Okay. Now the size of the s orbital is found to increase with the increase in the principal quantum number. So what is that? This suppose it is 1s. So this is the principal quantum number, and this is the orbital. Okay, so 1s is lesser than 2s, 2s is less than 3s, and 3s is less than 4s. Okay, so in this way you can also tell that which orbital is stronger or having higher energy. Next, the shape of p orbitals. So the p orbital consists like a lobes. So that is a dumbbell like. So this is about y axis, this is about z axis, and this is about x axis on either side of the plane passing through the nucleus. So this you can have to take like. So this is the plane and passing through this, and in between there is called nucleus. So this is about the shape of the p orbital, that is dumbbell, or otherwise you can call this as a lobe. Okay, nice. So as the lobes lie are along one of the x and y z axis, these 3 orbitals are given the designation 2px, 2py, 2pz. Okay, so each having one, that is 2px, 2py, 2pz. So we can say there are 3 p orbitals whose axes are mutually perpendicular. So there are 3 p orbitals called px, py, pz. So energy of p orbital increases with increase in the principal quantum number as that of s orbital. Same. Next, the shape of d orbitals. So the magnetic orbital quantum number for d orbital is given like -2, -1, 0, 1, 5. So hence we can say that there are 5 d orbitals. 5 d orbitals. This we have found through this magnetic quantum number. Okay, so this is so the orbitals are designated as dxy, d orbital xy plane, d orbital yz, d orbital zx or xz. So this is x square because it is on x to, that is symmetric. Okay, now this is also y square and this is dz square, that is. Okay, now so this will look like this one. So this is dxy and this is dyz and this is dxz. So we have information that d orbitals are 5, p orbitals are 3, s orbital is only 1. You understand my point? So the magnetic, I think repeated. Say okay, continue. So this is x square, y square, and this is z square. This is very peculiar in this way. Okay. So we have 1, 3, 5. What is 1? S orbital, 3 p orbitals, 5 d orbitals. So the energies of orbitals you can also have like this one. So 2s, 2p is having same shell. So 1s is k shell 2s2p L shell, 3s3p D, that is L M shell, and the other one is N shell. So now it is our duty to know the electronic configuration, that we call it as filling of orbitals in an atom. So the filling of electrons into the orbitals of different atoms takes place according to Aufbau principle. So basic is this. So this is followed on Pauli's exclusion principle, Ohm's rule, and that is relative and energies of the orbitals. So this Aufbau principle is used for filling of the electrons. This Aufbau principle in turn is based on Pauli's exclusion principle and Ohm's rule, and also follows the relative energies of the orbitals. So this principle states that in the ground state of the atoms, the orbitals are filled in the order of their energies. So these electrons have to be filled in orbitals based on the energy levels of the orbital. So the Pauli's exclusion principles. No two electrons in an atom can have the same set of quantum numbers, 4 quantum numbers. What are they? L, L, Ml and Ms. So this is the Pauli's exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers. So it can also be stated like that. Only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. What Pauli's exclusion principle says, 2 electrons may exist in one orbital like 1s. You understand? So one is having this. These two are opposite spins. Okay. So that is about this Pauli's exclusion principle. Okay. Next, the maximum number of electrons. The maximum number of electrons in the shell with the principal quantum number n is 2n square. So 2n square, where n is the principal quantum number. You understand? So if n is equal to 1, the number of electrons n is equal to 1 means K shell. So number of electrons is 2. N is equal to 2. So this is equal to 2n square, that is 8. So this is L shell. So n is equal to 3. So that is 3 square, 9, 80. So this is M shell. So that is also has to be known to you. Okay. So the maximum number of electrons in the K shell, that is n is equal to 1. So 2, n is equal to 2, 8, n is equal to 3, 18, and n is equal to 4, it is 32. Next, Wundt's rule of maximum multiplicity. So it states that the pairing of electrons in the orbitals belonging to the same sub-shell PDF does not take place until each orbital belonging to the subshell has got 1 electron each. What is that? So as we discussed just now, that P is having 3. Okay. So Px, Py, Pz. Okay. Now if P has to be, that is 2p 3, suppose if there are 3 electrons in the p orbitals, so these 3, in this we have to fill up like this only until it is filled, each shell subshell orbital is filled, that is px should be filled first. If there is a 2p2, suppose, so there is only 2, okay, so one is vacant for 2p2. For 2p1 it is, you understand? So if it is 2p4, okay, first you have to fill up all these three with a single electron, then come back to this and it is filled up, first one. So the order is X, Y, Z. Okay, so this is Hooke's rule. According to Hooke's rule, each subshell should have the one electron. Okay, so next one is, so the rule, what is that? This is the rule, what that is also called as a diagonal rule. 1s, then 2s, then 2p, 3s, and then 3p, 4s, then 3d, 4p, 5. Like that you have to fill up. So generally we write like this one: 2s, 2p, 3s, 3p, 3d. What? So according to energy levels. So just now we have discussed Aufbau principle. This follows the Pauli exclusion principle and Hooke's rule. Then relative energies of the orbitals. Okay. So this is about how to fill the electrons in orbitals. So the order with which the orbitals is followed like this one. So 1s, 2s, 2p, 3s, 3p, 4s, then 3d, like that. You understand? So don't follow numbers 1, 1, 2, 2, 3, 3, 3, like that. So this is called as diagonal rule. Okay. Now electronic configuration is nothing but distribution of electrons in different orbitals. So the first one is sp(d)6 notation. So we have hydrogen element. Okay, we will discuss in the next slide very comfortably. So we will now discuss that. So the electrons in the completely filled shell are called core electron, and the electrons outside these shells we call as valence electrons. So these electrons helps in forming the bonds and producing the isotopes, all these things. Okay. So for hydrogen, the atomic number is 1 and mass number or atomic weight is 1. So since Z is equal to 1, that is protons is equal to electrons. So you have only one electron that has to be filled with this 1s1. So 1s1, what 1s1 tells us? 1s1. 1 is the principal quantum number, that is also called as energy level, and this is the orbital, and this is called electrons. Okay, so how many electrons are there? In this helium, the Z is equal to 2, so you have 2 electrons that it has to be filled with. Next, lithium, it is 3, so 1s2 is filled first, then 2s1, like this one. So this we can discuss in the next video, that orbital diagram. So this will tells us more things than SPDF notation. What that? So just now I have said no, that is each orbital should be filled with at least one electron. Otherwise it will go wrong. Okay. First I will deal with the carbon. So carbon atomic number is 6 and it is represented by 6C. Okay. So what is that? So this is, it has to be filled with first. Now it is 2 over. The other 2 is also here. And okay. So this is K. This is A. Okay. So this has S shell should be filled first. Then only we want to come to the this one. So 4 are over. So 2 are remaining. So this should not be written like this one. Okay. So this should be written like only 1 and the other one is 2. The third one, suppose it is Z, it is vacant. Okay. So this is right. So each subshell should have at least 1 electron. So this is about carbon, and it is, I'll take up, this is neon, that is 10. So neon is equal to 10. So 10 means neon is represented by Nb. So 1s2, okay, 1 is over, 2s2 over, so 4 is over, so remaining are 6. First you will fill up this like this one. Okay, next to come back, this is 4, this is 5, this is 6. So all orbitals are filled. Okay, so this is about neon. The third is that is sodium. Sodium atomic number is 11. Okay, so this is represented by, that is Na. So you have to go like this one and like this, and okay, so 3p is over. After 2p, what is? We have to go, that is 3d, what? 6, 8, 10, it is 11. Got my point? 3d, no, it is 3s. So, okay, L have only 2. M have, in M it is 3s, 3d, sorry, 3p, then 3d like that. Okay, so first shell is S. So in this S there is only 1 electron. So this can be represented like this also. What is that? This is neon in bracket electronic configuration, and this is 3s1. So it is 10. So this is 11. So next one is magnesium. Magnesium is 12. Okay. So this can be written like this one, neon and then 3s2. So like that you can find out anything. So some of them I have written. These are called noble elements. These noble elements, the first one is helium, because it is having only one shell, and that shell is also has been filled up. And in neon, it is having only 2 shells, so that also have been filled up. Okay, argon it is 18, so it is 10, it is 2. 2 plus 8, 10. Okay, it is 10, this is 8, it is 18. The next noble element is krypton, that is 10, and 18 plus 18, it is 36. So like that you can develop. This is very useful in electronic configuration, but also used in, that is called chemical bond. Okay, thank you for watching.